Hello, we are 2021 RNA Chemistry 05, Park Seo-jun, Baek Jong-jin, Jo Min-ji. We are going to present about using covalent organic frameworks as cathode material and solid-state electrolyte in lithium-ion battery. Our contents are like this, and let's start with introduction. In the current world scenario, electronic devices and electric vehicles are key for sustainable future. And most of these devices and vehicles are powered by lithium-ion batteries. From the left graph, it is clear that lithium-ion battery technology uses is increasing over the years, while the cost of lithium-ion battery have decreased. Further, if we can connect renewable energy sources with battery for storing the renewable energy, it will lead to sustainable energy storage. Like this, lithium-ion battery has utility and sustainability. In lithium-ion battery, there are cathode and anode with external circuit. There is also separator between cathode and anode to prevent their contact. A typical lithium-ion battery contains lithium metal oxide as the cathode, such as lithium cobalt dioxide, and graphite as the anode. Liquid electrolyte is used enabling lithium ions to move from cathode to anode, from anode to cathode. Also, polypropylene-based porous separator is commonly used as the separator. However, there is a limitation of liquid electrolyte. It has narrow voltage windows, and there is also a flammability problem which can cause safety issue. Because of flammability of liquid electrolyte, thermal runaway events, then it can lead to safety issue. As the electrolyte is liquid, it dissolves active electrode material in electrolyte solution, which reduces cycle life. Therefore, we have to replace liquid electrolyte with the solid-state electrolyte. Solid-state electrolyte can be stable over the large voltage window and minimize flammability issue. Also, there is less chance of electrode material deactivation. For the solid-state electrolyte, we can use COF. COFs also can act as a cathode material and as a separator. Then what is COF? COF, which is covalent organic framework, is long network of porous, stable, and crystalline materials. As COF is composed of covalent bonding, it has stable structure and high chemical stability and thermal stability. As it is organic system, we can easily modify COF in a way we want. Also, it is framework, thus it has certain size of pore and permanent porosity. If we stack COF in a layered system, this layered COF is a suitable tunnel for lithium ion. Therefore, it can act as a separator.
Now I will introduce COF synthesis and characterization. For the synthesis of COFs, we use TB and PD, which stands for triphenylbenzene and phenylenediamine. TB and PD with these solvents here undergo a condensation reaction to first form a polymeric network, which in 3 days and solvothermal conditions turns into crystalline framework. So, the right upper side is the IL COF we get from the reaction, and if it is treated with elemental sulfur in 350 degrees Celsius for 1 day, it gives a TL COF as you can see in the below. On the left side, this is a picture of the IL and TL COF is synthesized using this process. The color of the two COFs appear different. The IL COF with imine bond linkage appeared yellowish green, while the TL COF with thiazole linkage appeared yellow. Let me show the COF structure modeling. These COFs were structurally modeled to get an insight into pore size and interlayer distance as shown in the figure. First, the IL COF has a pore size of 1.8 nanometers, and the interlayer distance of the IL COF is 3.4 angstrom. The second structure model shows the TL COF, and as you can see, the pore size of the TL COF is 1.9 nanometers, and the interlayer distance is 3.4 angstrom. These are only simulated structures, which are not refined as per X-ray diffraction patterns. We characterize a COF to synthesize using iris spectroscopy, PXRD, BT, TGA, SCM, and EDS mapping. First, infrared spectra can provide information about the functional groups present by measuring their bond vibrational motion. We use air as background, and in the IR data, as you can see on the left side, the two below graphs, which shows TB and PD IR spectra, we were able to identify CO double bond peak in TB and NH peak in PD. But after synthesizing COFs, in the TL COF and IL COF, we cannot see any of the monomers peaks. Instead, we can see new peaks like imine bond peak. To conclude, we found that carbonyl stretch from TB and NH stretch from PD disappeared after reaction, while a new peak at 1,620 per centimeter appeared related to imine bond formation. And this indicates complete COF formation. However, it was hard to recognize sulfur from the IR spectrum, so we are planning to do solid-state NMR later on to make sure that sulfur is in the COF. From PXRD, on the right side, as you can see, it appears the IL COF is highly crystalline, while TL COF is only moderately crystalline. The respective reflections are shown in the graph. In the red curve, peak at 4.8 degree represents the pore size in the COF, and is related to 100 reflection, while a small peak at 26 degree represents tacking interaction in COF. From the graph, IL COF is highly crystalline because of very sharp peak, while the TL COF shows less crystalline because the peak is not as sharp. Therefore, we can conclude that more purification is needed for the TL COF. From the surface area measurements using BET method, both COFs were found to be porous. We can say that the COFs are porous. The measurement of surface area, tentative pore size, and the total pore volume are shown in the chart here. It shows that the IL COF has bigger surface area than the TL COF. IL COF has a surface area of 862.32, while TL COF has a surface area of 353.22. The tentative pore size of the IL COF and the TL COF was 2 nanometers. The total pore volume of IL COF was 0.9315, while the TL COF has 0.1848 volume. From thermogravimetric analysis, TGA, on the right side, it is found that both COFs are relatively stable until around 500 Celsius degrees under anti-atmosphere, and the TL COF shows slightly more stability than the IL COF, and after around 500 degrees, the structural decomposition occurs. From SCM images, it was observed that both COF particles are micrometer sized, where IL COF appeared globular shaped and TL COF appeared with flower-like morphology. And both COF particles were aggregated. These two COFs show different morphology, and morphology is very important to use the COF for some application. From EDS, energy dispersive spectroscopy mapping, it is found that IL COF contains only nitrogen, while TL COF contains both nitrogen and sulfur. It is because the IL COF has imine linkage, while the TL COF has diazo linkage. From all of this analysis, it can be said that both COFs are synthesized with negligible impurity, moderate to high crystallinity, and permanent porosity.
After we synthesized IL COF and TL COF, we made COF-coated cathode. To prepare COF electrode, we mix COF, Super P, and PVDF in 60-30-10 ratio. Here, Super P acts as a conducting material because it has pi conjugated network of carbon, thus it can increase conductivity. And PVDF has high chemical and electrochemical stability and sticky character, so it is used as a binder. However, if we add PVDF too much, it can lower the conductivity, so we use only 10%. Then we add NMP as a solvent, which can mix the material and make a uniform slurry. We put zirconium ball or stirring ball into the mixture and go through mixing machine for 20 minutes. Then we can apply the mixture on the copper foil, which we fix on the glass plate with tape. After that, we put the glass in the oven and wait for a day for drying. After drying, we cut the electrode in a round shape and move the antechamber. In the antechamber, dry it under the vacuum at 80 degrees Celsius for 12 hours. Then put the electrode into glove box. Now we are going to make 2 lithium-ion batteries with different electrolyte and solvents, which are 1 mole lithium TFSI in DOLDME and other is 1 mole lithium PF6 in ECDMC. We use glass fiber-based GFC separator with outer cap, spring, and separator, and cough-coated copper cathode and lithium foil on the stainless steel as anode. We can make coin cell. Lastly, by mechanical pressing, cell was sealed and kept 12 hours to attain equilibrium.
In this page, we'll discuss about electrochemical impedance spectroscopy. In general, from EIS, we know that the diameter of semicircle represents charge transfer resistance. Then this linear part at low frequency means lithium-ion diffusion. And finally, the starting point at high frequency means solution resistance. So we can say that for ILCOF, charge transfer resistance is higher for lithium PF61. Then for TLCOF, charge transfer resistance is similar for both electrolytes. Then this page, we will discuss about cyclic voltammetry cycle. Red one is for ILCOF and blue one is for TLCOF. Then we will see ILCOF-based lithium-ion battery using 1 mole lithium TFSI in DOLDME for solution. In the first cycle, we can see some peaks on this charging process. We assume the reason is the decomposition of electrolyte. Electrolyte decomposition can also occur at low voltage, and this could lead to formation of a stable layer called solid electrolyte interface. Then after first cycle, all cycles show similar shape, so we can think it is stable. Then we can see 2 peaks on discharging process. The first one is for lithiation of imine bonds, and second is for lithiation of pi electrons. Since pi electrons is more stronger, it occurs at higher voltage. Then for charging process, the first peak is for pi electrons delithiation, and second peak is for imine bond delithiation. Then we can analyze this for another graphs like this. Then this page we will discuss about galvanostatic cycling in TLCOF. Let's see these 2 graphs. We use different solution for 2 cells. The above one, we use 1 mole lithium TFSI in DOLDME, and the below one, we use 1 mole lithium PF6 in ECDMC. Then below shows similar capacity for first cycle and 25th cycle, but DOLDME one is not. So we can assume that 1 mole lithium PF6 in ECDMC is more stable for TLCOF. Then we can see that for facts for this cycle, different solutions shows different performance. We think that the reason why as different electrolyte composition might form different kind of SEI layer.
Now we can make cough pellet and for solid state electrolyte. To make cough pellet, we have to add around 10 mg of the cough powder to a stainless steel die. Then press it at 16 megapascal for 1 hour. To measure the thickness, we use caliper and we get around 100 micrometer value of thickness. We put SE films in the temperature controllable vacuum chamber of a glove box and dry at 120 degrees Celsius for 12 hours. Then store it in the argon atmosphere in the glove box before cell assembly. Before we make full cell, we made symmetric cell to test the stability of the half cell. We coated lithium foil on a stainless steel. We used cough assay film and add 20 micrometer 1 mole lithium TFSI in DOLDME to make it more conductive. In the other side of stainless steel electrode, we coated lithium foil on aluminum foil and complete the symmetric solid-state lithium-ion battery. There is graph of deposition and stripping of this symmetric cell. The data are recorded at room temperature for lithium deposition and stripping. We applied current density of 0.1 milliampere square centimeter, 1 hour for stripping and 1 hour for deposition. Further analysis will be done, and COF acid film will be checked for cracks to check the stability.
For summary, in this research, we learned the synthesis and characterization of two COFs, L-COF and TR-COF. We used several analysis to characterization the COFs like PXRD, IR, SEM, BT, and TGA. We learned how to use COFs as cathode to make a lithium-ion battery. We learned to use basic electrochemical techniques to study the charge-discharge behavior of COFs-based lithium-ion battery. For our further plan, our immediate plan is to make a functional solid-state battery using COFs as solid-state electrolyte. We will perform chemical electrochemical stability studies of COF solid-state electrolytes. Our final goal is to make a fuel cell using COFs as the solid-state electrolyte. Then thank you for listening our presentation.